Welcome to day 8 of our Explainer series. A lot of developers treat traditional RAG, Retrieval-Augmented Generation, like it's some sort of magic bullet for model hallucinations. The thought process is usually pretty simple. Just attach a vector database, and boom, your model is perfectly grounded, right? Well, not exactly. Real-world complexity actually exposes a pretty major flaw in that exact design.
Because what happens when that vector database simply doesn't have the answer? Or what if you get a prompt that requires pulling database records, then doing some math, and then maybe checking a live web feed? A static retrieval system just breaks down entirely. So by the end of this explainer, you're going to see exactly how shifting from passive retrieval over to an agentic workflow completely solves this problem.
Let's think about it this way. Imagine traditional RAG as a highly efficient but entirely static archivist. You ask a question, and the archivist goes to a very specific filing cabinet, pulls out a file, and reads it back to you. But if the answer isn't in that specific file, they just shrug. They honestly don't know. They are incredibly good at finding exactly what they're told to find, but they have absolutely zero ability to pivot. Agentic RAG, on the other hand, is completely different. It's much more like hiring a relentless, highly capable research assistant. If their filing cabinet is empty, they don't just give up. They'll open up a web browser, they'll grab a calculator, they might even query another department. They actively design a workflow to hunt down the solution, and they adapt to roadblocks in real time.
To make that happen, we need a massive shift in how we actually use the foundation model. It's no longer just a passive text generator, sitting there guessing the next word. Instead, it becomes a reasoning engine. Basically, we give the model a prompt, plus a whole menu of available tools. Then, the model evaluates the problem and autonomously decides its very next move. It actually thinks rather than just speaks. So instead of immediately drafting a final, polished response to the user, the model pauses. It plans out a sequence of actions. It figures out exactly what pieces of information are missing, and then decides which specific tool is best suited to go retrieve each of those missing pieces.
So let's look at the actual mechanics of this. What are these external tools we're talking about? Well, traditional RAG is usually just hardwired to a single vector database. An agent, however, wears a whole utility belt. It can trigger a vector search for past documents, sure, but it can also call web APIs to pull breaking news. It can invoke math calculators to handle strict arithmetic without hallucinating the numbers. It can call your internal enterprise APIs to check live inventory. It can even delegate specific subtasks to other specialized AI agents inside a multi-agent network. It dynamically strings all these tools together, depending entirely on what that specific user prompt demands. Technically speaking, this architecture operates in a continuous loop. First up, the user query comes in. Second is LLM reasoning. This is where the model breaks the larger problem down into smaller subtasks. Third is tool execution, where it actually fires off the API or the database call. But step 4 is really where the magic happens: observation and self-correction. The agent actively looks at the tool's output. If that web search returned an error, or if the database record came back completely empty, the agent doesn't just crash and throw an error to the user. It loops back. It tries a different tool. It essentially fixes its own mistakes before you ever even see a response. Let's actually see this in the real world. Imagine asking a standard standalone base model about a recent event that happened outside of its training data, like, say, the 2024 US Open. It hits a wall immediately. It will very likely output a hallucination, or it'll simply just say something like, "The event has not been announced, therefore I do not know the answer to this question." It is entirely stuck behind its knowledge cutoff. Now, to bypass that wall, a data scientist might orchestrate an agentic workflow using a framework like LangChain. For instance, they could drop in IBM Granite to act as the central reasoning engine, use an open-source ChromaDB to hold recent documents, and utilize IBM Slate models for the embeddings. From there, we hand the Granite model a custom tool. Let's call it a US Open Context Retriever, and we literally teach the model how to use it. Suddenly, we have a highly practical recipe for dynamic problem solving. If we look under the hood, the system prompt is forcing a very strict logic loop. First, the model explicitly outputs a thought, something like, "I need to find the location of the event." It then outputs an action, which is triggering our custom retriever tool. The system then runs that tool and returns an observation with the correct stadium data right back into the model's context window. The agent then validates this new piece of data, and finally, armed with the actual facts, it generates a perfectly accurate answer. So, to wrap all of this up, Agents turn LLMs from passive text generators into highly dynamic problem solvers. By giving a foundation model a reasoning loop and a diverse toolkit, you completely shatter the hard boundaries of its training data. But, it does leave us with a pretty interesting question. If an AI can autonomously research a problem, test various tools, and actually correct its own logic errors on the fly, what does that ultimately mean for the future of software engineering as a whole?